In this exercise, let's take a look at how we can use rotational equilibrium and sum of torques equals zero to help us to solve problems. So in this exercise, we're asked to find a couple things here. The tension in this cable, as well as the horizontal and vertical components of the force exerted on this beam at the wall. So there's like maybe some force in the x direction here and some force in the y direction that the wall is exerting onto the beam. So we're supposed to find this tension here and these forces. So there's three unknowns that we have here. Let's first start out by, we're looking for forces, right? So we should start with a free body diagram, and now we can expand our free body diagrams to include some of torques, right? So the free body diagrams start to look a little bit different, in which case we need to take the shape of them in consideration as well. So free body diagram of the bar, because I'm interested in the forces acting on the bar, and it looks like we have tension here going this way, and we have some, I'll call this H, like a hinge in the X and a hinge in the Y. There's a 300 Newton barrel kind of just pulling off of here. And there's also a weight of the beam. It's 150 newtons, and its center of gravity is at its geometric center. So it would be right here, right? So we also have another 150 newtons acting down here. And we should dimension these as well. And so if I could essentially place my origin right here, or not even essentially, I do place my origin here, and the 150 newtons would be 2 meters from the origin, which is at the hinge, and then the 300 newtons is another 2 meters beyond that, and it's something like this. And then we can have this, we actually have an angle theta here, and we could solve for this angle. This angle is 37 degrees. Just from, the theta is equal to the arctan of 3/4. We could also actually say here that we ultimately want sine and cosine of t to break our forces into components. We actually know the sine is going to be 3/5, so it's 3/5, and the cosine is 4/5, 4/5, 0.8. But if you wanted to just solve the angle there instead, that's what it would be, with some rounding error in there. So when we take the sum of so actually let me call this, I'll call it theta, is about equal to 37 degrees. And now we look at this, like as I pointed out here, we have three unknowns. We have t, we know the angle, right? So that's nice. And there's another unknown. We need hy and we need hx. So we have three unknowns. We must have three equations. Well, previously free body diagrams would give us two equations. Sum of forces in the x direction equals 0. Sum of forces in the y direction equals 0, right? But now, since we also have rotational equilibrium, if this bar is completely in equilibrium, both of these are true, as well as the sum of the torques around any point. We get to choose a point. Any point is equal to 0. Okay? So typically I like to start out with the sum of the torques, because the reason for this is that I get to choose any point I want. I get to take the sum of the torques around any point. So if I choose to take the sum of the torques around a point that has a bunch of unknown forces going through it, I don't really have to include those, because remember, the torque caused by a force going through that point is 0, right? So I can take the sum of the torques around any of these points. I can take the sum of the torques around a point here, but that one's going to be, it's just algebraically inconvenient, right? Because I have a lot of extra, well, maybe not extra forces, but I have a lot of forces to consider, right? I got to consider the 150, the 300, the hy, the t, which actually I'll break this t into like a ty and a tx. So actually tx and hx go through that point. I wouldn't have to consider those, but there's more convenient places. I could choose to take it some of the torques around here, and I wouldn't have to include the 150, but I know the 150, so that's not really that inconvenient to include that one. I could actually even choose a point like down here. I can take the sum of the torques around here, but that's even more inconvenient still, because now I have to include TX and HX and all these. So, there's a couple places I could say I think that it's going to be more convenient, or most convenient, to either take the sum of the torques around here, so T passes through here, I don't need to consider T, or I can take the sum of the torques around here. I think I said sum of forces a second ago. Sum of torques around this point, so T doesn't cause any torque, or take the sum of the torques around the hinge here, so these reactions at the hinge these forces at the hinge don't cause any torque. So I would pick one of those, although you can really do any point you want. But I like to start with that one because then it just makes the equations easier. I can remove some of my unknowns off the get-go. At least in the first equation, I can solve for one thing. So let's take the sum of the torques around the hinge. That'll be most logical, I think. So taking the sum of the torques around the hinge, this hinge right here, this is equal to, I have 150. This is going to be clockwise, right? So this is negative 150 newtons times 2 meters. And then I have the 300 newtons, that's also clockwise, so minus 300 newtons times 4 meters, right? This was a 4 meters there. And then Ty, this is going to be counterclockwise, so that's plus. And again, the lever arm is 4 meters, so plus 4 meters, actually, let me call it Ty times 4 meters. And that would be all the forces that cause torques. I could say plus Hx times 0, right? The moment arm is 0. And they could also say plus Tx times 0 as well. Because remember, Tx, it's not the distance to the force, it's distance to the line of action of the force. So the line of action goes right through here. And there's no distance, there's no perpendicular distance between the hinge and the line of action of Tx. Tx goes right through it. So there's actually no torque created there. So all of this equals 0. I'm just going to get rid of these for clarity. So equals 0. And so we can solve for Ty. So Ty, or actually I can just note here, let's just say that, noting that Ty is equal to T sine of 37, which is, well, there's actually a slight little bit of error using that. It's like, so it's probably better to use, and I wouldn't take off points if you have just a slight little rounding error there. But we said the sine was actually 3/5. So 3 over 5, so that's 0.6. So this is actually equal to 0.6 T. So then, what we end up with here is that T is equal to 4 times 300 plus 2 times 150 divided by 4 times 0.6. The 4 came from there. So this is T is equal to 625 newtons. And so now we have tension, right? So we were able to find the tension just from the sum of torques about the hinge. And once we've used one of these equations, you can't use it again. It's actually not a unique equation. You have to, I can't take the sum of the torques around another point. Well, I can't continue just taking sum of torques around different points to solve all of these. At some point you have to use the sum of the forces as well. So next we use the sum of the forces, and it doesn't matter. We can use the x direction here. That's simple. So summing the forces in the x direction equals 0. And so then we have the only forces in the x direction are hx and tx, right? So we have hx minus tx equals 0. So we have hx is equal to tx, which is equal to t cosine theta, which we say cosine was theta of theta was 0.8, so this is 0.8 t. And t we know is 625 now. So the force that the hinge exerts in the horizontal direction comes out to 500 newtons. And then lastly, we need to find out the y component of that hinge force, right? Hy. We need this one here. And so we can just sum the forces in the y direction to find this. So summing the forces in the y direction equals 0. This is hy plus ty minus 150 minus 300 equals 0. And so hy is equal to 150 plus 300 plus ty was, remember this is t times sine theta, which was 0.6, so 0.6 t, so plus 0.6 times 625. Oops, sorry, that's actually a minus. And then hy is equal to, this comes out to 75 newtons. And there you have it. So, you know, we can now solve more complicated free body diagrams because now we have another equation we can use. So that's what usefulness of having rotational equilibrium as well.